Recording's rolling. It's Friday, October 17th. We're going to finish this rotational kinematic lab from yesterday. So, you guys remember that involved this turntable, okay, and there were two parts of the story. So, here's a quick recap. So, the first part of the story is actually, I got to do the setup first. Okay? The setup first is you have some mass that's some distance from the center, okay? And you measure what is that at radial distance. Okay? And then you give this three full rotations at constant angular velocity, and you time that with a stopwatch. Okay? So for three full revolutions, then you let it go, and it naturally slowed to a stop. And you measured with a protractor how far around it went in degrees. But you guys remember, by the time we get to the formulas, you can't use the angles in degrees in the formulas. You have to use angles measured in what? Radians. Yeah, radians, right? Okay, so let's quick recap there. Okay. Here. Where is this? So there might be a few minutes at the end of class, so do some quick posts with you guys. And then, guys, what you do by the time you come to class on Monday morning? Yeah, 8 classroom. So I'll debrief that with you guys. All right, so now my numbers will be different than your numbers, but I had my coin 13 centimeters from center, so I put radius 13 centimeters. Oh, okay. No. Right, so three revolutions. Guys, one revolution, which is equal to 360 degrees. How many radians is one revolution? 2 pi. Yeah, 2 pi radians. Okay. Therefore, three revolutions, that's where the 6 pi is coming from. 6 pi radians. Okay. Now, I did that for 5.9 seconds on the stopwatch. Then I let it go. Okay. And guys, if you divide radians by seconds, does that give you radians per second? Yeah. And the numbers follow. That gives you an angular velocity, radians per second. Okay. Now, as soon as I let it go, the stopwatch stopped. Okay. And then this particular one, it looks like it went more than a full revolution around because I know 6.28 radians would represent one revolution. This is more than that. Okay. Yeah, yours may not have done that. That's okay. But somebody got to use the protractor to figure out how far. We converted degrees to radians. Guys, how do you convert degrees into radians? Like how many degrees equal to how many radians? Huh? Oh, yeah, okay, so one radian could be about 57.3 degrees. That's one way to do it. I think I had you guys do 180 degrees is equal to pi radians. You can also do 360 degrees is 2 pi radians. And how we did. Just remember radians. Okay. Okay, now from that, if you know how far it went to stop, is that this theta here, but it has to be in radians. Has to be radians. And you also know, well, guys, if you a stop, what's the final angular velocity? 0. And you also know how fast it was going right when you let it go, because isn't that this right here? Isn't that this right here? How fast it was spinning? Okay. Isn't that 3 kinematic values? Could you solve for this alpha, which is angular acceleration, the rate that it's slowing down to get to a stop? Can you solve for this alpha? Okay. We did that, and that's how we came up with this right here, which is negative, and I gave you the negative just to really emphasize and remind you guys this would be negative. Of course, it would be negative anyway. Okay. So mine came out to this many radians per second squared. Okay. You guys got your alpha, of course, you got your day. Okay. And then, guys, once you have your alpha, can you take that up to the second kinematic right here and say, again, I know it's going to 0 radians per second from however fast I'm spinning it. And I just found alpha so I can plug in. Can you solve for time? Solve for the stopping time. Solve for the stopping time? All right, you guys do that too? Okay. And I think that's the last thing we did yesterday. Pretty close to the last thing. So you guys got to there? Yeah. Solve for the stopping time? Okay. All right, and then the bells ring in and okay, good. How about this? Let's do some graphs and we'll come back and get the linear values later. Let's do some graphs. So, hey, look, we got it. Displacement, velocity, and acceleration versus time. Only these are all the angular values. It says theta, omega, and alpha. So angular displacement. Yeah, let's start with that middle graph. Angular velocity versus time. Guys, label your vertical axis omega for angular velocity, and let's put this in radians per second. Okay. So you guys know graphs convey information. So whoever's reading your graph needs to know what that graph represents. Like what values are you talking about? And I did throw one time on there. T naught. Now that is the moment that you take your hand off and you let it start slowing to a stop. Right? But this first interval of time, you're letting it rotate at a constant angular velocity. Guys, what does constant angular velocity look like on an angular velocity graph? How many guys think it looks like a constant? Yeah, it's a constant, a flat constant. Just might look like that all the way up to 2 knots. Okay. Oh, and I can write a value. Guys, what value do I write on my graph right here? It's like that, 3.19. Right? Now, of course, your number is probably different, but it's however fast it was rotating and radians per second. You guys see why that makes sense? Right? So that's the first three revolutions, three rotations, it's just constant angular velocity. Okay? And then right at this moment, you take your hand off and let it naturally slow to a stop. Yes, slow to a stop means that final angular velocity is going to be what? Zero, which is all the way down here. Okay? Let's see if I can get this approximately to scale. Because I know I was rotating it myself manually for almost 6 seconds. Isn't that true? This T naught, 5.9 seconds right here. Right here. I should label this also. Let's go time in seconds. Okay. Can you label both axes? Okay. So variable unit. Everybody's got their axes labeled for sure, right? Okay. So 5.9 seconds. Took my hand off. And then, now here's where the calculation comes in. Guys remember, this is the last thing I think you guys did before the bell yesterday, is you calculated the stopping time. Now that's in addition to the original time on the graph it would be. So if we took an additional 4.6 seconds to slow to a stop, what is 5, 9 plus 4, 6? That would make the whole process last 10.5 seconds. So I'll go up to 10.5 seconds, which is probably right about there. Okay? And I'll say it goes to zero final angular velocity. Guys, how does it connect? Is it a straight line? Right? Yeah, as long as it slows uniformly to a stop, it's a straight line. And that is our default assumption in this class. Okay. Now, realistically, it's probably pretty close to that. Right, sir? Okay. Okay, so it was rotating at a constant angular velocity for a while. Then you take your hand off and it slowed your stop. That's all. That's okay, right? Okay, how about let's do angular acceleration. So let's label this alpha for angular acceleration, and the unit's going to be radians per second squared. Now, this is like an upside down flippy graph. I put the time axis way up here. So time in seconds is like way up here. Oh, maybe these are like negative values or something's negative. What about the first interval? Because if when you had constant angular velocity for the first few seconds, what was the angular acceleration equal to?
Zero.
Zero. Yeah. Zero, right there. There was no angular acceleration. It wasn't speeding up or slowing down, rotating. It was just rotating at a constant rate. So there was no angular acceleration. Okay. Then, when it's slowing to a stop, guess what property of velocity versus time tells you acceleration versus time? The slope. Do you see a negative slope up here? Negative slope? Actually, I know a value. Isn't it this number right here? Definitely negative. And mine is negative 0.69 radians per second squared. And that was for the last few seconds. During the last about 4.5 seconds on mine. That thing. Okay. Now, of course, the numbers on your graph are different than numbers on my graphs, right? But your graphs should take the same shape as my graphs are taking. Okay. Okay. Everybody good so far? Where I'm getting all these parts of the graphs from? Right here. Okay, here's a recap. Okay. So there was constant angular velocity for a while, and then it slowed to a stop. Okay. In terms of angular acceleration, well, during the first few seconds, there was no angular acceleration because it was rotating at a constant angular speed. And then when I took my hand off and it slowed to a stop, okay, it was slowing to a stop. It's moving in the forward direction, the acceleration is negative. Okay. And we're going to assume in this class that's a constant value. Right? That's a default assumption in this class. So we have constant acceleration values. You guys see a bunch of those. Okay. Now finally, let's do theta, angular displacement in radians as a function of time and seconds. Okay. So how far did it rotate as the time's ticking along? Sure. And let's start this at 0.0. So let's say at time 0, it hasn't moved anywhere yet. Well, at least not that we're counting, right? So maybe it's gotten in motion, right? And maybe we start the stopwatch right here to start timing it. You guys remember start the stopwatch? Okay. Now, go ahead. See if you guys can get the whole graph. Right? Of course, there's two halves of the story. There's two halves of the story. Right, I'm going to take a trip around the room and see if you can correctly draw that graph. Okay. Both parts. The first half where it was going constant angular velocity, and then when it was slow into a stop. Right, that's two halves of the story. If you have a pencil, then that'd be good. In case you get it wrong, you can erase it. But think you get it right. Here, I'll tell you what this is analogous to in a linear sense. Okay, so could this be analogous to a car is just driving at cruise control for a while and then slams on the brakes and brakes to a stop? Okay. Because no, that was a couple of months back ago in this class. A couple of months ago. Um, but it's the same graph shape, but now it's just a different story with different. Yeah, all right. Ryan got it. Winner. All right, who else got this? Ryan got it completely. Right. Close. Some of you guys are close, but not quite there. Not quite. Ah, yeah, Lily got it. It's good. All right. Yeah, yeah. Felipe got it. All right. Michael got it. Yeah, Richard got it. All right, Andrew got it. Okay. Yeah, Chase got it. Ooh, close, almost. Okay. Yeah, a bunch of you guys are getting this. A bunch of you guys are getting this. All right, nice. Yeah. So, what a bunch of you guys figured out is that while it's rotating at constant angular velocity, is it accumulating angular distance at a constant rate? And does that just look like zip, like a straight line? Right. I mean, this does correspond to this, right? Also zero acceleration, right? Something like that. Right. But then when you take your hand off and let it slow to stop, okay, slow to stop. See, here, give you guys a visual here. Okay. So when I had my hand on it, it was rotating counterclockwise. Counterclockwise is usually considered the positive direction. Okay. So it was rotating in the positive direction. Okay. Then I take my hand off, and is it still rotating in the positive direction? It did. Right? Guys, did this turn backwards? I'm going to go backwards now. Did it go backwards? No, it didn't go backwards. Right? So it kept rotating in the positive direction, just slower and slower and slower. Right? So still moving forward, just at a slower and slower rate. Guess what shape is that going to make right there? A parabola. Aha. Right? In fact, it'd be like an upside down parabola. And right at the top, guys, this point right here, right at the very end, is the what of the parabola? Vertex. Aha, vertex. That's your. Okay. Uh, Here's the second half of the story right here. I made this one a poster. Now, this is just the slowing to a stop part. So you have negative angular acceleration. You have an angular velocity that goes to zero. And the angular displacement, see, still moving forward. You're still accumulating positive angular displacement just at a slower and slower rate until finally it's this vertex, this parabola, comes to a stop. Okay, just like that. All right. So you guys good with those? With those? All right. Now, let's go fill in this one box we had over here. You guys see omega average? Like the average angular velocity? We almost never talk about average velocities in this class, but every once in a while it comes up. Okay? But you can see it really quickly from the graph. Okay? Now, guys, if I'm just looking at the average velocity during the part where it's slowing down, wouldn't that be like this midpoint right here? This midpoint? It's kind of like the average height velocity right here. And isn't that also, wouldn't that also be represented by half of the angular velocity that you're rotating at? Okay. So whatever I was rotating at, and in my case 3.19 radians per second, I'm going to say divide by 2, 1.59, something like that. I'm rounding a little bit. It's good, okay. That was like between going fast to going to a stop, the average value. You guys good? Yeah, with that rate. Okay. Right, now, how about all these linear boxes here? Okay, so remember what's going on here is that all the numbers we got so far and all the graphs so far are talking about angular values, angular displacement, how far is it turned, angular velocity, angular acceleration. Okay. But what if you were interested in a single point. And you say, not how many turns is it made, but could you imagine if this was a car driving around a big old circular racetrack, ooh, and the odometer is adding up, ooh, driving around? Like what sort of circumference distance has it gone? Like a distance in meters? And guys, all you do is take the angular displacement in radians, multiplied by your distance from the center, and that tells you how far you've gone, like in a linear, like the odometer reading on the car. I said, you do the same thing for velocity and same thing for acceleration. Okay. So let's try that. Here is your angular, your initial angular displacement was 6 pi radians. That's 3 revolutions of 6 pi radians, right? Okay. Oh, guys, if I had that coin 13 centimeters out, can I just say this theta times this r gives me this distance? Can I just do that? Okay. So I take my 6 pi radians of rotation, I multiply by 13 centimeters from the center, and it tells me 245 centimeters. Right? Now, if you also had a coin at 13 centimeters out, then that means your coin also went 245 centimeters total. Right? But it's about 2.5 meter sticks. Ooh, that's pretty good distance, isn't it? 2.5 meter sticks. Yeah. It's not we take a meter stick and curl it into a circle. At least in my brain, it doesn't necessarily perceive it as a full meter long, so it's kind of deceptive. But yeah, like about 2.5 meters it went almost. Right? If you set a radius at like say 9 or 10 centimeters, it would not have gone as far. Right? Better. How about velocity? Can I take my 3.19 radians per second, multiply by 13 centimeters out, and it tells me 41.5 centimeters per second. I'm rounding a little bit, Okay. Okay. So if I had a speed gate set up, and the coin goes through the speed gate is going to read about 41 meters per second, or centimeters per second. 41 centimeters per second. Like as a linear speed, as a tangential speed. Okay. Is there any questions so far? All I did in the last two calculations is this theta times this r to get this x, and then this omega times this r to get this v. That's it. Okay. How about the stopping distance? Okay. So again, car on a circular track might be, if you're braking to a stop, if you straighten that out to a straight line and say what distance is that? Okay, that's what this is right here. So I'm going to take my 7.38 radian that it was rotating to a stop and multiply by 13 centimeters. And my braking distance is about 96, and I'll round it to the nearest centimeter there because it's really close. So anyway, okay, about 96 centimeters to brake to a stop. That's almost a full meter. But I can believe that because see, I have a radius 13 centimeters out, and I saw it make more than one revolution to come to a stop. So almost a meter. Yeah, that looks about right. It's about a meter. All right. Your guys' numbers are working too? You guys see where I'm getting all these from? Huh? Who has a question? No? Okay. Yeah. How about this? How about this average right here? Do you think you take the average angular velocity and multiply it by r, which for me 13 foot, about 21 centimeters per second, something like that. And then how about angular acceleration? Ooh, that's funny. So if I went the linear acceleration, sort of like the rate the car would be braking into a stop, I could do it that way. Right? All I have to do is take the angular acceleration and multiply by radius. So here's my angular acceleration, negative 0.69. I'm going to multiply that by the radial distance of 13 centimeters. Sure. Right, guys, good? Right. Negative 8.79. Well, I'll round that to negative 9.0. It's pretty close. Pretty. 8.97. All right, you guys good? Centimeters per second squared. All right, that all good? Okay. Before we do this graphs, let me ask you guys this. Because this acceleration you just wrote at the very end, this linear acceleration, is that a centripetal acceleration? Yes or no? Is that centripetal acceleration?
No.
No. How about this angular acceleration? Is that centripetal acceleration?
Yes.
No. Uh, there are two different kinds of acceleration. So the tangential acceleration, this is the first kind of acceleration you guys learned. It's like the rate you could be speeding up or slowing down in a straight line. That's the last number you just wrote on your table. I just went over with you guys. Okay, that's the first kind you learned about. Okay. That's in meters per second squared. Okay. Now, this alpha right here is angular acceleration. That's the rate the entire turntable can be changing at angular velocity. So the rate, so in this case, it'd be slowing down at some rate. And that's in radians per second squared. Okay. Guys, nowhere on this table yet have you ever written anything about centripetal acceleration. That's a different concept. That's the acceleration associated with the centripetal force that is always directed towards the center, that keeps it on a curved path, okay, which I didn't make a box for. I never made a box for that on this. Okay. But actually, the centripetal acceleration is a lot more applicable to the lab on the back side of the page. Okay, so this turntable version, which we're going to save for next week. Okay. All right, guys, good. 30. All right, that right? Okay, so now let's do these linear graphs. Linear graphs. So x versus t. Guys, could this be x in centimeters versus time in seconds? Let's go ahead and label all the axes. Could this be linear velocity in centimeters per second and time in seconds? And then linear acceleration in centimeters per second squared, or tangential acceleration, if you like, as a function of time in seconds. Okay. Do you guys just label all your axes? Okay. Guys, looking at your guys' work and bios over the last few weeks, about half of you guys are pretty good at always labeling your axes. Okay? You guys, if you haven't been in the habit of doing that, then definitely start doing that from here on out, including, of course, when you take the exam. Okay? Because remember, graphs convey information. So you have to tell whoever's looking at your graph, what are you talking about? What variables, measured in what units? Because it tells you something. Okay. So let's start with the middle one and branch out. I usually do anyway. So velocity versus time. So wasn't it true that I had my Roosevelt going at like 41 and a half centimeters per second? And that was a constant speed. Constant speed. I wouldn't say constant velocity because it was changing direction, but constant speed of 41.5 centimeters per second. Okay. And that was true during the first few seconds, during the first 5.9 seconds for that matter. I can label that 5.9 seconds here. Okay. And then I took my hand off and let it slow to a stop. Well, if that was a car driving around a big old driveway, it's sort of like the car slamming on the brakes, but still turning the steering wheel, but it's slamming on the brakes. That's what we're thinking in terms of like linear speed. It does go to zero. In fact, it did that at for mine, it's the 10.5 second mark, because I know it was an additional 4.6 seconds to come to a stop. Calculated that. Okay. Guys, guess what? Guess how that gets? Is that a straight line? Straight line. They normally are in this class. Velocity versus time, normally straight lines. How about acceleration versus time? Okay, so we got the variables and units already labeled. So I'll put 5.9 seconds here. Maybe there's something special happening at the very end mark, 10.5 seconds. Guys, what was the tangential, like the linear tangential acceleration while it was going at constant angular velocity? Was there any? No, because it wasn't speeding up or slowing down. So this is just zero. Right? Now, was there a centripetal acceleration? Yeah, there was. There was centripetal. There was this going on right here. You could do either v squared divided by r or omega squared times r. It would tell you the same number. Actually, we should probably calculate that anyway. Right? But that's just not asked in this graph. That's not what this graph says. This graph's on about angular acceleration. Or sorry, about linear acceleration. Still zero anyway. Okay. And then down here, could I put negative 9.0 centimeters per second squared? Go like this. And it brings to a stop. Hey, did you guys notice the pattern between the left graph and the right graph? Are these exactly the same shapes as each other? Yeah. Because I know why that would be. I know why that would be. Because, guys, to go from angular to linear, all you do is multiplied by r. You scale it up by, in my case, 13 centimeters, or in your case, whatever your radius was. Okay? But it's some constant value. Okay? So these graphs are exactly the same shape as each other. The velocity graphs, the acceleration graphs. Okay? Now, of course, they communicate different information with different units in different numerical values. But the graph shapes are identical. You guys getting that too? Because take this one, multiply by 13 centimeters, you get this one. Take this one, multiply by 13 centimeters, you get this one. That's all. Okay. So, what do you guys think the x versus t is going to look like? Yeah, let's go. Trying to keep an eye on the clock here. I've got. Wait, when do we get out of here? I always get confused. We're 40. Oh, 43. Yeah, thanks. Okay. We got about 15 minutes. Right here. Okay, so I think it's going to look like this. Zoop. Okay. Now that goes up to 245 centimeters right there. 245. Pick right here. Okay, and then it's still okay. Then I take my hand off and it's still rotating forwards, just slower. And right, let's just stop. 5.9 seconds. This is 10.5 seconds. Okay, and it stops finally at an additional 96 centimeters. So it's 245 plus 96, at 341, like 341 centimeters. So that's like the total distance it went. Like it was the total odometer reading on the car. If you give it that. Okay. That's good. All right. All right. So let's go back and fill in this question right here. I wonder what was centripetal acceleration. Let's just do it during the part where the first half of the story. Remember, you were rotating at constant angular velocity for a while? Okay. Could you imagine if you were a ladybug that landed right on that point while it was spinning? Woo, woo, woo. It would feel like somebody turned the gravity up and maybe shifted it sideways a little bit, or something like that. Okay. So I wonder what was the centripetal acceleration. And there's two ways we can get it. So I'll do for the first half of the story here. Right here. I'll say centripetal acceleration equals. Okay. So here's two ways. We could either do omega squared times r or v squared divided by r. Okay? So let's start with omega squared times r. So I'm going to take this omega, which is 3.19, that's radians per second. I'm going to square that and multiply by my radius of 13 centimeters. Okay. Now, keep in mind, if I type in the numbers exactly like that, what are the units on the answer going to be? Is it meters per second squared or centimeters per second squared? Yeah, it's got to be centimeters per second squared because I typed in centimeters. Okay, so just as long as you know that and you communicate that. I'm getting 132. 132, that's centimeters per second squared. Okay, that's centripetal acceleration. Okay. Guys, what's Earth gravity in centimeters per second squared? Is it 980? Right, 980? Right? So I wonder what this is compared to Earth gravity of 980 centimeters per second squared. About 0.13, so like 13%. Okay, so it's kind of like, again, if you were that ladybug, you'd feel pulled down by your full weight, as you always are. Right? But also, it feels like there's some kind of sideways force that's about 13% of gravity, 13% of your weight. Okay. And in your rotating frame of reference, you think it's throwing you out, but really isn't it some kind of force, maybe friction force or something that's actually pulling you into a circle? Okay, something like that. How about let's try this other way. Let's do v squared divided by r. Because here's my v. So let's try centripetal acceleration with that method. So I'm going to take 41.5 centimeters per second, square that, and divide by 13 centimeters. Okay? Now I'm going to get the same units for centimeters per second squared, which means that this number should pretty well match this number. Now I have been rounding a little bit here and there, so if it's not the same, okay. So we're going to see how close this is to 132. You guys got that? It should be pretty close to 132, because that's what I got with the other method. Two methods down here. Yeah, it is. It's 132 centimeters per second squared. It's the same thing. So whether you do v squared divided by r or omega squared times r, both ways tell you the centripetal acceleration. Okay. You guys good? All right. Is there any question about any part of that story? Okay. So, guys, hold on to this paper because next week we'll do the turntable friction lab. Okay, so more turntables next week. We check out all this today. All right. Now, since we we have about 12 or so minutes. Let's do some puzzle. Here's puzzles. Puzzles. Okay. Now, in my last AP class, we ended up doing number two. There's basically two categories of puzzles here. There's some that look like There's some that look like a lot like your last lab with a plate of canisters. And here's a good picture, okay, with these blocks on the table and the string. Okay, that looks like your last lab, doesn't it? Plate of canisters. Okay. And number two actually follows that model. There are also some questions, especially on the back side, that involve gravitation. Like, oh, guys, look at this. What would the magnitude of acceleration due to gravity be if Earth's mass were changed by some factor, or Earth's radius were changed by some factor? Like, four-point question. Okay. So we got some circular motion, centrifugal force questions, and we got some gravitation questions. So number two, an airplane is traveling due north. It makes a turn to head due east, completing the turn in a uniform circular motion with a radius of 200 meters. And it's and a centrifugal acceleration of 1g. Right now, once they give you that last detail, combined with everything else, the radius and so on, you can calculate everything else that you want, like the speed of the plane, how fast is the plane going to achieve that outcome. Also, how much time does that take to make that 90-degree turn to go from north to east? Take some time, right? Right, you guys have a premise? Okay. Here, I'll draw it out. Draw that. So this is number two. Okay. Let's get a plane going here. Get a plane. Okay. And the plane's just going straight north. Right. At some speed. I'll call it speed v. Right. As a tangential velocity, like a speed. Right. And it's just going. And then it makes a turn. Turn. Right. And then it's going east. Right. So here, and then the plane ends up pointing this way. Okay. And now it's going east. Okay. I'll say the entire time it kept the same linear speed. So the same v. Okay. Now, I'm not going to say the same velocity. Guys, why would I say it's the same speed but not the same velocity? Because what's changing?
The direction.
The direction. Direction changing. Okay. We can have the same speed. So if you're down on the ground and you point a radar gun at the plane, like right here, is it still reading the same speed as it always was? Yeah. So the speed's always the same. Okay. So they gave you some values. I'll say given. They told you, let's see, the radius of curvature was 200 centimeters. So I'll call it capital R, like a fixed R, is 200 centimeters, meters. Whoops, we're doing meters now. 200 meters. They also gave you the acceleration is 1g.
Is the progress check just like a completion grade?
Yeah. And guys, what do you feel like using for gravity today? What number do you want to use? 10? Okay. 10 meters per second squared. All right, we'll do that. Yeah. Okay. So let's treat this as given though. And we want to find v, the speed of the plane, and also t, the amount of time it takes to get from here to here. Okay. Okay. Do you guys see I could fit a circle flush this curve? Like right about like that. You guys see a circle flush to that curve? Okay. And it's got some radius. Got some radius right here. Call it radius r. In fact, they told us the radius. It's at 200 meters. Right, guys, yeah. Right. Now what? Okay. Can you guys think of a formula that might connect all these variables together and let you actually solve for v? Bam! Exactly. Okay. And actually, it's the only version of this that they actually give on the AP equations. So it's right here. AC is v squared over r. Yeah. If you want the force version of that centrifugal force, you have to multiply by mass m. And if you want the angular version of that in terms of omega, you have to substitute in this expression up here. Right? Yeah. Centrifugal acceleration in terms of linear speed is v squared over r. So let's throw that on the board. Centrifugal acceleration is v squared over r. So we got that. Okay. Oh, well, we do have to solve for v, solve for speed. Oh, hey, and we have a and we have r. Isn't that true? Right. Isn't it true when they say you're accelerating at 1g? Right. Like if you're sitting inside the plane, it feels like somebody turned the gravity. If you had an accelerometer, you're like, okay, yes, gravity's still pulling you down, but also there's one G sort of pulling you to the side, or at least it's pulling you this way, but it feels like it's that way. So okay, let's solve this in terms of variables. Can you guys solve for V in terms of variables? Is it? Yeah, that's that. Okay. Right, and let's put some numbers in. So we plug in 10 meters per second squared and 200 meters radius. So square root 2000. Okay, I'm getting like 44.7 thereabouts. Guys, is that my answer? Is it 44.7 or am I forgetting something?
You're getting units.
Ah, units. Ah, yeah. There you go. Yeah, units. Okay. That's how fast the plane is flying. You go around this curve and experience 1 g of sideways acceleration. Okay, that right? Okay, good. Okay. Now the other question is, how much time does that take? How much time? Here, switching code. How much time does it take just to complete this curve part of the trip? Like this quarter of a circle. Guys, would that be a quarter of a circle right there? A quarter of a circle? Huh. So if you know how fast it's going, and you know the radius of the circle, and you're going a quarter of the way around the circle, is there enough information there to solve for how much time that takes? Guys, what's a good equation that it should play off? Distance equals speed times time. Okay, just do that. Distance equals speed times time. Right. And then is this distance is a quarter of a circle. So isn't that like well, a quarter of the circumference, I should say. A quarter of the circumference, is that right? Is equal to speed times time. Okay. Now we want to solve for time. Okay, what is the circumference in terms of the radius? Circumference equals 2 pi r. Okay. So half of 2 pi r. Okay, so now I have it in terms of radius, which was the given value. And we just found v. I can solve for t. Yeah. Is that? Okay, let me clean this up a bit. Half of, or sorry, whoops, guys, I made a mistake. Okay, what mistake did I just make? It's not half the circle, it's what? A quarter. Change this. Oops, it's a quarter of the circle. Something's off there. A quarter of the circle. Okay. Alright, so divide down the v, I'm getting time is equal to big fraction. Okay. So I got a pi up here, I got an r up here, a 2 over 4 divides to 1 over 2, and divide down the v. Okay. So there's the answer in terms of variables. And then we can plug everything in. So in place of r, we're going to plug in 200 meters. In place of v, I'll put in 44.7 meters per second. Pi 200 over 2 44.7. Okay. I'm getting the amount of time it takes is 7.0 seconds. You guys say that same thing? About right. About 80 seconds. Yeah. All right. How about this? What would it feel like inside the plane? Or maybe here's a better way to quantify that. I suppose you're sitting on a bathroom scale in on your seat. Okay. So here's you like sitting here, like hanging out. Okay. And let's say you have a mat here. I'm just gonna make up a mouse. Suppose you have a mouse for like 60 kilograms, and therefore you have a weight of. What would your weight be about? Yeah, 600 newtons. Is that right? And with the normal force from the seat, just be balancing out, and that would be the scale reading, which would also tell you 600 newtons. Is that right? Now, because that right there is when the plane is going constant velocity, which could be like right here. Or here for that matter. Okay. But guys, what about when you go into this turn? Do you think the whole plane turns or like tilts some angle? How many think if you're being pulled down with 1 g of actual gravity and to the side with 1 g of the pivotal, how many guys think that the whole plane and the seat tilts at 45 degrees? And then here's your free body diagram.
Yeah.
So you got your normal 600 newtons pulling down. But guys, the normal force is the normal force the same as before or much bigger? Much bigger. So that I know we're getting short on time, but I'll finish this real fast. If you add these tips to tail, I'll use a parallelogram. I don't do that very often. Okay? The net effect right here would have to be 600 newtons. Guys, if this is 600 and this is 600, can you do some trigonometry and figure out the scale reading on the scale? Is it Pythagorean? 600 squared plus 600 squared square root, which, by the way, is the same thing as 600 square root 2, or 849 newtons. Okay. So when they say you experience a sideways centripetal acceleration of 1 g, okay. Really, this is a more detailed version of what's run if you're sitting on a scale. Okay. All right. So yeah, we have about half a minute left. So let's call that a wrap right there. And by the time you guys come in on Monday, have 80 classroom finished.